Okay, so we're back here in the folder for Lecture 5, Social Interactions. Let's look now at the catastrophe model. So I'm going to open that in Vensim. This one is interesting. I think I want to say no here. Let's say no. I think just for the scaling. Say no again. All right, yeah, this will probably do it. Let me max out the screen. And so this model it's interesting. It's got three cohorts: a cohort of young people, cohort of adult people, and a cohort of elderly people. And of course, these cohorts exchange, one matures to the other. So I'll walk you through a description of the model, and we'll look at some of the units and see what the results are. But essentially, the young are born, okay, and the born is driven by a birth rate, and it's driven by the availability of adults. So a young population doesn't reproduce, adults reproduce, and the young become adults through maturity, and we're going to see a little bit of how that happens in the dialog boxes. The adults, further age and become elderly, and the elderly pass away. Okay. Now, the reason this model has a catastrophe is that because it has it's got a flux out of the adult pool, the adult population pool. It's called a catastrophe, and I'm gonna look at that first, just to illustrate what the issue is. And the issue is that there is a pulse. In year 2005, it lasts for a year, and it loses 100,000 adults. So there is an event that causes 100,000 immediate deaths in the adult population. And the idea of this, of this model is to see what that does to the overall population. So let's walk a little bit through the entire model, and let's start with the young. So the young are essentially they're born, and then they become mature, or they can actually die. So this model actually has, the units of this are people. So this model actually has a death of young people. So there could be an accident or something that causes young people to die. Okay, so there's a young people mortality rate that's given, based on whatever demographic data you have, or whatever data you have, and there's a maturity, which is it's a factor that is used to define when there is a transition in being from young to adult. So this defines a period of maturity, which in this case the period of maturity here is 25 years. So 25 years is in this model, it's the period of time it takes for a young person to become an adult. So you become an adult at 25 years old, and for the purposes of this model. Okay. The young can die. Okay. As I said again, or they can become mature, and those are the two ways that young people decrease stock. Okay. So let's look at adults now. The adults are fed by the young through maturity. Okay, so if you look at the adult equation, there's maturity feeds into that. Then adults die either of old age, or through a catastrophe. So if you look at the schematic again, the adults become old and become elderly, or they die. Okay, they can die, or they can die due to this catastrophe, which we just indicated was a pulse. Okay, 100,000 people are removed in 2005 from the pool of adults. Then if we look at the elderly, okay, the elderly are fed by aging adults, and then are decreased due to natural deaths. Okay, and the natural deaths are driven by a so-called final period, which is let's take a look at that variable. Final period, it's a period of years. So after they become elderly, actually I don't think there's a period of aging here that I didn't go through. 60 years. So at 60 years, an adult becomes an elderly, and 30 years after that, it can be considered to be, to die due to natural causes. Okay, so that's the way people die of old age. If there's an additional auxiliary variable here, there's a total population that is calculated by adding adults, the young and the elderly, so you can actually keep track of that. So that's essentially the picture, okay? In a nutshell, you have a 3-cohort population of young, adults, and elderly that mature over time. So the one becomes the other. But in the middle, there are extracts. The young can die, or they become mature. Okay. The adults can die. They can become old, but there's also a catastrophe that takes out 100,000 people. And then the elderly can essentially die of natural causes by themselves. The adults produce offspring through births, so that's another variable. And those are essentially the dynamics. 25 years of maturity, 60 years to become an elderly. There's a catastrophe. One thing that I didn't mention was the initial values. And if we go to the stocks, so the young initial population is 400,000. For the adults, it's 500,000, and for the elderly, it's 100,000. So that's the initial state of the population. And if you look at the model settings, you can see that it's a 100-year model from 2000 to 2100. Time step is 1 year. You can change that, but that's pretty much the setup, and you can then run the model. So you can just do a simulation, and the simulation is done very quickly. And now we can go to the graphs and see what happens. So let's take first a look at adults. I think that's because those are the ones that undergo the catastrophe. And if you look at the graph for adults, you can see here what we were referring to. The adults start at 500. During the first 5 years until 2005, the adult population is going down. That probably means that a lot of them are becoming old. Okay, but then all of a sudden the population takes a dip. It loses 100,000, and then after that it sort of starts recovering over time, and it sort of plateaus out at a little bit over 400,000, and that's the adults. Okay, we can look at the elderly. Okay, and look at the graph. And the graph for the elderly is continuously increasing. So what's happening in this population is that the adults are aging, and so the population of elderly is going to plateau somewhere near 200,000 people. Okay, so because of adults, and it's interesting to see that the catastrophe that adults undergo doesn't seem to affect much, the elderly population. Let's take a look at the young. Look at the young and graph it. It's interesting because this actually it's very reflective of what happened. This actually picks up on the signal from the adults. The younger are, they're born, they start growing and becoming more as adults reproduce. Then the adults in 2005 take the hit for the catastrophe, and that makes the young population drops after that effect disappears, and then this sort of plateaus out at started at 400,000. Remember the young, it ends up being less than that. So the lasting effect of this catastrophe is that the young population never quite recovers. Okay, and so the effect keeps going on. And if you look at the total population graph, so now this is the the total, the young plus the adult plus the elderly, you can see that the population as a whole does tend to recover. There's it grows at the beginning of the first 5 years, and it takes the catastrophic hit, and then it starts growing. Now, what we saw is that this growth is primarily driven by the adults that were larger to begin with. They were 500,000 to begin with, becoming elderly. So the lasting effects is that you have a a population that this recovers from the catastrophe but becomes older on the average. Okay, so that's an interesting interesting demographic effect of this catastrophe. So again, with this model, you can do many of the same things that you can do with other models. You can create input-outputs. You can create custom graphs. You can do variable inputs. So I'll let you play with this and look at how these cohorts interact. You can fool around a little bit with the maturity and aging periods, with the death rate. So you have a whole host of variables here that you can toy around with. So hopefully you'll be doing that, that will conclude the discussion of this model, and I'm going to move on to the next one.